And then we're going to switch to the file system. I guess we can finish the file system, and I'm not sure we're going to have time to work on the I/O system. Maybe we can. I can actually just cover part of the material for the file system, main part of the material, and then cover the I/O systems. Okay. This semester is kind of interesting. We have they spread the spring semester all over the you know spring break all over the semester. So so we lost a couple of days. Okay. So any questions before we move forward? Okay. Let's continue to talk about the page replacement algorithm. So we mentioned that in the memory management, so using the demanding page, then we can load the page into the physical memory if it is necessary. So because of this, we can support more processes with the limited physical memory space. So actually, we can actually have a much larger virtual memory space than the physical memory space, because we don't have to load all the pages into the physical memory. Now, because of this, then we actually run into a couple kind of issues. Since we can support a larger virtual memory than the actual physical memory, then in certain cases, the physical memory may be full, so maybe they don't have enough physical memory space. Now, if one more page is called, if one of the instructions in a page is called, and the page is not currently loaded into the physical memory, then you have to figure out a way to replace the page. So we have to pick a victim in the physical memory and pick one of the page in the physical memory and replace with the page that the request for memory. Now that requires the page replacement algorithm. So last time we talked about a couple of other page replacement algorithm. One is the optimal. Okay. So the optimal basically, replace the page in the reference string that's the farthest in the future. So in this particular example, the reference string, that's the actually reference string of pages. So the page will be called in such a sequence: 20314101 230. So we assume that there are 4 frames in the physical memory. Now this is a very sorry. So we assume that there are 4 frames in the physical memory space. That's a simplified version of this algorithm. And currently, page 0 is loaded into frame 0. Page 1 is loaded into frame 1, and the page 2 loaded into frame 2. So that means all the frames are loaded with pages. So the current memory is full. And now we assume that the page 0 was loaded into the frame number 0, and the page 0 is the first page that was loaded into the frame. And the page 1 is the next one, and the page 2 is the next one, and the page 3 is the last page that was loaded into the frame. So then, in order to actually run this, so we need to create a queue. The queue gonna actually place each of the page in there. Okay. Now, for the optimal, because we already know that if we have, in this particular case, like in this sequence reference string of page, now, so the current page are loaded already, 0 to 3 are already loaded. So if the next, for whatever the reason, the instruction of the next page was called, so we have a page reference for 2. And now if page 2 is actually called, and then the operating system going to check whether page 2 is in the physical memory. And in this case, yes, page 2 is actually in frame number 2. So there's no page fault, right? And then in this case, if page 0 is called, and there's no page fault because 0 is already in there. And also for page 3, page 1, each of these pages are in the physical memory. Now, the next page that will be referenced is page 4. And then we check page 4 is not in the physical memory. So then we have page fault. Okay. Now, if page fault happens, if we use optimal, we're going to check each of the pages in the memory to see which one will be called first in the future. Okay. So then we check each of this one. 0 will be called over here. And 1 will be called immediately. And 2 will be called here. And 3 is the first, right? So in that case, with the optimal page replacement algorithm, we're going to replace 3. Okay, so 4 will be placed here. And 0, 1, 2 still going to be kept. Okay. And then no wonder, so the next couple of pages, there will never be incur any page fault because we replace the pages that will be referenced first in the future. So all the pages nearby, they are already in the memory. So this is actually optimal is optimal, right? You're going to dramatically reduce the number of page faults. Now, we find out optimal is the best page replacement algorithm. However, for also the optimal is not really feasible. It's not realistic because you have to have the knowledge of the complete page reference string. So that means we need to know, which instruction will be called next. No, so we have to actually, make sure at the compiler time we know exactly the sequence of the page that will be loaded. So which is not really possible because for some of the dynamic linking algorithm, you don't know which page will be loaded next. Okay, so optimal is not realistic. So then we come up with the FIFO, first come, first serve. Okay, so the FIFO actually basically replace the, the oldest one in the physical memory. So this 4, we have no page fault, right? Now, once actually page 4 is referenced, and then we can basically check which one is at the header. So suppose page 0 is loaded at first, then page 1, page 2, page 3. So every time using FIFO, when a reference, when a page fault happens, the incoming page will actually will replace the page at the actual head of the queue because 0 was loaded into memory, and this page 0 was the first one that was loaded into the memory. So we're basically going to replace the 0 with 4. So we'll replace 0 with 4. Instead of optimal, replace 3 with 4. So that's the FIFO. Now, once you replace 0, then 0 was replaced. And now 1 becomes the first page in the queue. And the 4 will be the last one. So we actually push everything forward. Okay. Push everything forward. And if next time when page replacement is requested, then you will replace the page number 1. Okay. So now next one in the page reference string is 1, and the 1 is actually currently in the memory, so there's no page fault, right? And then it comes with page 0. Unfortunately, page 0 was replaced over here. Page 0 was replaced, so you have to replace the page 0 back. And then we're going to continue. So in that case, FIFO is really not a good page replacement algorithm. The only, if you can say what's the advantage of FIFO, the only good thing about a FIFO is it's simple. It's very simple to implement. Okay. Now the next one is called least recently used. Okay. That's something we're going to talk about right now. So the least recently used one okay. So for the least recently used algorithm, now what we're going to do is suppose that initially page 0 was loaded first, and then page 1, page 2, page 3. So page 0 is at the header. Okay. Now the least recently used page replacement algorithm is going to actually update the queue frequently, even though the page is actually in the physical memory. Now, in this case, for example, the first actually page referenced the page is 2. Now 2 is actually in the frame, right? But 2 is actually, a third page on the row. So that means if you have to replace the page, you replace page 0. If they have to replace the next page, you're going to replace page 1. And then if you have to replace next page, you have to replace page 2. Because page 2 is, third page on the row. Now, with least recently page replacement algorithm, now every time when a page is referenced, so in this case, page 2 is referenced. So we don't have page fault, right? Because page 2 is actually in the memory. But if page 2 is referenced, then the chance that the page 2 will be replaced are going to be reduced, because page 2 is recently, used. So it's recently referenced. So in that case, now we're going to actually, once actually page 2 is referenced, then we're going to update the queue. And we're going to put the page 2 at the end of the queue, and push 3 forward and push 2 back. So this is going to actually say, now page 2 was recently referenced. So it was recently used. Okay, with the least recently used page replacement, if the page is recently used, don't replace it. Okay, so then we put the page 2 on at the end of the queue. Okay, now next page that will be referenced is page 0. Now page 0 is also in the memory. So we don't actually have any page fault. However, this is going to actually put the page 0 at the tail. Because page 0, if at this time, if we have a page replacement over here, page 0 will be the one that will be replaced. But fortunately, page 0 at this time was referenced, and which is in the queue. And then the page 0 is recently referenced. So I'm going to put the page 0 at the tail. So that means now there's no risk for page 0 to be replaced. So when I put the page 0 on the back and I push the rest of the page forward, so 1 going to be pushed forward, and 3 going to be pushed forward, and 2 going to be pushed forward. So in that queue, 0 is at the tail. So next page is coming, and if there's a page fault, then the page will be replaced is not 0 anymore because 0 was recently referenced and recently used. Okay. Again, page 3 is referenced, which is also in the queue. So I can put the page 3 back. And 1 is still here, and I push 2 forward, push 0 forward. And now 3 was recently referenced, so I put the 3 on the tail. Okay. So then 1 is referenced, which is here already in the frame. So page 1 is referenced. So I put the page 1 at the tail and push 2 forward, push 0 forward, push 3 forward. Okay. So now 2 is actually pushed to the head. Okay. So now we have page replacement happens because 4 is actually not in the memory. So page 4 is not in the memory, so we have to pick a victim. Now, which one we're gonna pick? We pick 2. Okay, so we pick 2. So 4 gonna replace 2. Okay. And then we're gonna push all the page forward and put the 4 at the tail because 4 was recently uploaded to the memory, so it was recently used. Okay, so the bottom line is all the pages at the head is the least recently used. Okay, and at the tail, the page at the tail was most recently used. So 4 was most recently used. So that's why every time when we have a page replacement, always replace the one at the head. Okay. Now next the page is 1, which is in the memory. So we don't have page fault, right? Okay, we don't have page fault. Okay, I should put 4 here, and there's a page fault. We don't have page fault. However, we're gonna update the queue because 1 is referenced. So that means I'm gonna actually put the 1 at the end, and yeah, 0 is still here, 3 is still here, 1 actually put on the back, and the 4 will be pushed forward. Okay, so now we have 0, 3, 4, 1. Okay. Now 0 is referenced, so then we're going to push 0 at the back, 3, 4, 1. Okay, 1 is referenced, so we push 1 to the back, 0, 4, 3. Okay. Now 2 is referenced. Okay, so that means 2 is not in the memory, so we're going to replace 3. Okay, replace. So 2 will be replaced here, and the 0, 1, 4, and then push everything forward and put the 2 at the back. Okay. And then there's another page replacement because 3 is actually not in the memory. So we replace 4 with 3. 4 is the bottom. And keep other pages. And the 4 is replaced. Okay. So that means 0 push everything else back forward. Okay. And there's no page replacement because 0 is in the memory. But this is going to actually push for the 0 to the tail of the queue. Okay. So basically, every time when a page is referenced, you check the page whether the page is in the frame, in the physical memory. If it's in the physical memory, no page fault. However, because that page is referenced, so you're going to actually put the page at the tail of the queue, and push the other extra page forward. Okay, so this basically gave you some kind of idea that if the page is actually more frequently referenced, then that page will less likely be replaced. If the page is more frequently used, then it's less likely the page will be replaced, which is good. Okay. Also, this is actually the least recently used actually page replacement algorithm is based on our life experience. Okay. Now, we may actually have some kind of experience, for example. So if you actually manage some of the documents, okay, you have a couple of actually books or documents or anything, and then you suddenly reference this document. You actually have to actually use the document and pull the document out and then read the document, and then you use the document. And then if the document is used, and there's a bigger chance that you're going to use the document again. I don't know why, but that's the case. Now, if one of document has never been used for a long time, the chances that this document will never be used. Okay. Again, that's based on life experience. Another example is that if you actually meet someone, if you meet someone in a party, and then both of you exchange the information, say, okay, I'm glad to meet you, and here's my business card, and here's your business card, here's my phone number, and then you keep the phone number, you get the phone number from the guys in a party. And then the next day, you feel like, oh, I really like, the conversations with this guy. So I want to actually, call him or call her. So you just pick up the phone and call the guy. Now, if you pick up a phone and call, so then most likely you're going to actually call this person again. Okay. If you get the phone number, I just feel like, no, I'm not going to contact the guy again. So most likely you're going to put this phone aside and never going to call this person. That's basically some kind of life experience. Okay. Now, the least recently used page replacement algorithm is based on this kind of idea. So if the page has been recently referenced, then for whatever reason, this page will most likely will be referenced again. So that means you don't want to replace the page, because if the page was recently referenced, and it's likely going to be referenced again. Now, if you replace it, then you have to actually, once actually you reference the page again, then you have to, put the page back. Okay, so you're going to have to go through the page fault. So So the chance is that if the page has never been used for a long time, then replace the page, because the chances that this page will never be used again. So that's, there's no proof, but that's the reality, you know. So a frequently used page will be used again. So okay, so that's the least recently used algorithm. Now, the least recently used algorithm is really a good algorithm. Not as good as optimal, but because you replace the page based on history, so it's realistic, it's doable. Unlike optimal, which you actually have the knowledge, you should have a knowledge of the future of these, you know, execution. So least recently used algorithm is doable. However, there's a problem, because if you use the least recently LRU, least recently used algorithm, then every time when a page is referenced, then you need to actually check, you know, each of the algorithm and check which one should be, you know, replaced. So because every time when you do this, you're gonna actually update, the queue. Remember, so the most the, when you reference the page, even if the page is in the physical memory, then you have to update the queue to reflect this, because then you have to put this page at the tail of the queue. So this is a lot of work, because every time when the page is referenced, you have to update the queue. So that's a lot of work. So that's a reason why people think LRU is a good algorithm, but there's a performance issue. It's not really efficient in practice. So that's the reason why people actually design some algorithm which is not exactly LRU, but approximations of the LRU. Okay. Now in this actually, in the design of the replacement for LRU, then we need to actually introduce some kind of new concept. One is the reference bit. Okay, it's called R bit. A reference bit is a bit associated with a page and is set automatically by hardware whenever the page is referenced by any instruction. Okay. Remember, we actually mentioned that reference bit. It's also called a dirty bit, right? Once the page is loaded into the physical frame, then if the page is referenced, that means the page has been used. Okay. And then we put the mark on the page. So with LRU, if the page is referenced, then you should put the page at the tail of the queue, so it will not be replaced. Okay. Now the other thing we're going to introduce is the aging register. The aging register is associated with a page and is shifted periodically to the right by 1 bit. Okay. Unless the most significant bit is set to 1. Okay. Now we're going to actually discuss this aging bit using an example. Okay. So now the next one we're going to talk about is called the aging page replacement algorithm. Okay. Now the aging page replacement algorithm does not maintain pages sorted in exact LRU order. So we don't have to maintain this exactly the queue. Okay. We don't have to maintain the queue. Every time one page is referenced, then we actually update the queue and to reflect the reference. But with aging, we don't do this. And we don't do this for every page reference, but we actually periodically do it. Okay, so we actually put a groups together, um, you know. So the aging replacement algorithm does not maintain pages sorted in the exact order, but it groups together pages referenced during the period of the consecutive references. Okay. So we only update the order periodically after D consecutive references. Okay. Now, what is D? D could be 20, could be 50. So that means within actually 20 page references, we don't update the queue. And only after we reach number 20, then we'll update the queue. And then after next 20 page references, we update the queue. After next 20 page reference, we update the queue. Now, if we set to 50, then it's every 50 times the page reference happens, then we update the queue. Okay. So this is going to replace the frequency of updating the information. Okay. So here, let's take a look at the example. Let's say D equals 50. And then we use 4-bit aging register. Okay. Now, when you use 4-bit aging register, what does this mean? So that means using 4-bit, if the 4-bit contains 000, so that means, let's take a look at like this case, 0100. Okay. So that means the page has not been accessed or referenced during the last 50 most recent reference because it is 0. However, the page was referenced during the, for the last 50 page reference because the bit is 0, so that means it's not referenced. But in the last 51 to 100, the bit is 1, so that means page was referenced during the past 51 to 100 page reference. Okay, so now with D equals 50, so that means if it's all 0 for the aging register, that means in the last 200 page reference, nothing has been changed. So that means the page, if the page actually has 4 zeros with D equals 50, that means during the last 200 references, the page has not been accessed or referenced. Okay. Okay, so that's what this means. So indicates the page has not been accessed during the last 200 references. Now how are we going to use this in our page replacement algorithm? Again, we're going to actually assume there's a 4 pages, page 0, 1, 2, 3 for each page. And the reference bit was all set to 0. So that means the page was not referenced. And the aging all set to 0. What does that mean? So that means all this page has never been referenced. Okay. So that means probably this is actually the initial state when the program is just loaded into the physical memory, right? So at that time, all the page reference bit is 0, are 0. And the aging, look at the history, it's all 0. Okay, So that's the initial state. Page 0 to 3 are resident. The R bits and the aging register all contain 0. So that's the beginning. Okay, after dereference, now remember, suppose D is 50, okay? After 50 references, the R bit shows that the page 0, page 2, and page 3 has been accessed or referenced at least once. Okay. It could be referenced once or could be referenced 20 times, but it doesn't matter. Within the last page reference, last 50 page references, if the page has been referenced once or twice or 3 times, it doesn't matter. As far as it's referenced, the R bit changed to 1. Okay. So you only actually just count, in the last 50 page references, whether the page has been referenced or not. It doesn't matter how many times the page has been referenced because you cannot tell because it's only 1. Okay. You cannot tell whether it's referenced once or referenced 20 times. Okay. So that's the current situation for the last actually 20 references. 20 references. Now these 3 pages has been accessed or referenced. And then what the next thing you're going to do is, now after the 20 references, then you're going to actually shift this R bit to the left, and all aging rest shifted to the right, and the R bits are shifted into the most significant position. So this is the most significant position for the aging register. So you have 4 bits of aging register. Okay. Now this reference bit will be shifted to the most significant position in the aging list. Okay. That's after actually 50 references. Okay. And then here comes another 50 references. Okay, next, in the next dereferences. So the next actually 50 references. Now page 1 and 2 were accessed. Okay. Again, I don't know whether how many times it has been referenced, but they are referenced. Now page 0 and 3 has never been referenced. Okay. Now once the 50 references is reached, so that means combined with the 50 reference initially, now at this time, you have reached a total of 100 page references, right? Once you reach the 100 page references, then what you do is, okay, so you're going to push these to the right. So push the first most significant bit to the right. Okay. And then add the most recent page reference to the most significant position. So then this one pushed to the right, and the most recent one added to the most significant one. Okay. Now that's at the time 100 references. Now if we continue, if during that time, so here we have the reference bit is set to 0 after 100 references. And then the aging bits, age register looks like this. Okay. So then if next time page fault happens, now we have to replace one of the pages. Okay. Page 0, 1, 2, 3. Which one will be replaced? Now, what do you think? Which one will be replaced?
I think either page 0 or page 3. They're both the same, so they probably have to pick one like at random, but they're the smallest out of all of those.
Okay. Now, page 0 or page 3 will be replaced because if you look at the number, these are the smallest number. If you actually, for this 4-bit, if you actually look at the value for this 4-bit, and this is actually 4, corresponding decimal value 4, that's 8, right? And this is actually 12, and this is a 4. So the smallest number basically means, okay, looks like in the past 100 references, all the pages are referenced. All the pages are referenced. However, now this page 2 has been referenced the most. It's referenced in the first actually 50 reference period, and also referenced in the second 50 reference period. So this one was frequently referenced, so don't replace that one. Now the next one, this one was recently referenced, even though this is actually in the first actually 50 period, 50 actual reference period. It's not referenced, but it's recently referenced. Now this too has been referenced in the first 50 reference period, but both of these are not referenced in the second, 50 reference period, you know. So these two should be replaced. Okay. Now, because they are the, now suppose, if you have a page replacement at this moment, these two should be replaced. Okay. Now, if there's no page replacement happens, then if you continue, and then the next page reference is, this. Okay. So during the next reference, page 0 and 3 are accessed, and the same steps shifted and then resetting the R value and then repeat. Let me see. Okay, so here, I think I just repeat this, and so next in the next actually D reference, that means from reference 101 to 150, then page 0 and 3 has been referenced. Okay. So now we push these, aging extra bit to the right, and then replace the recent, page reference in the most significant bit. Now, this actually dramatically changed the way that the page replacement is going to do, because now page 0 and 3 has been referenced. So if page reference happens at this time, then we will find out the page 1 will be replaced, right? Because page 1 has the smallest number. So we basically keep this aging register and the reference register. In the reference register record in the past 50 reference, if D is 50, in the past page, 50 page references, If the page has been referenced, then you update the referenced page, referenced actually bit. Now, then after the 50 actually page reference period is reached, then you update the aging register by shifting all the actually numbers to the right, the bits to the right, and put the most recent reference bit into the most significant bit in the aging register. So you're going to push forward. Now this is going to keep record. If the page is if the page is most recently referenced or recently accessed, so then the value at the most significant bit is 1. So that means this value, the value for the aging register is bigger, right? So that means if here's a 0, it's actually smaller than the bit with 1. So that's why we actually keep pushing the bits to the right, and the most significant bit in the aging register, it always keep the if it's referenced, then that number is always bigger because the value is going to be 1 over here. So if a page fault occurs, then all registers are compared. The page with the smallest value is selected. So when you actually compare, you compare the aging register as a whole 4 bits. So this is actually 10. This is 4 plus 2, that's 6. That's 4, and that's 10. Okay, so this won't be replaced. So the aging page replacement algorithm is almost the same as LRU, but instead of actually each time you update the value, then you actually update the value every 50 page reference. So within the page 50 page reference, you only update the R bit, the reference bit. Okay, you don't actually change the aging register. And once that 50 is reached, then the R bit is placed in the most significant bit, and then the rest of the actual bits will be moved, shifted to the right. Okay, so keep doing this. So this can actually reduce the chance that the queue is actually updated. So it's a good replacement for the LRU, and it's actually works very well. Now, there's another actually variations for the LRU page replacement algorithm. It's called a second chance page replacement algorithm. Okay. Now, if you want to actually draw this very quickly, second chance page replacement algorithm is almost like a FIFO, except you put a reference bit for each page. Okay, if you put the reference bit for each page. So let's say this is the head of the queue. That's the tail. Okay, so if the page is actually zeros here, 1, 3, 4, 8, 7, so that's the page. So based on the FIFO, the page at the header will be replaced, right? But each page is also associated with a reference bit. Okay, suppose the reference bit is 1 here, 1 here, 0 here, 1, 0, 1. So that means page 0 is at the header based on the FIFO. However, page 0 was referenced. Okay, now in that case, if page replacement happens, the algorithm is going to check, okay, the first one in the head, the page in the head, at the head, and also check the reference bit. If the reference bit is 1, I'm going to say, oh, even though page 0 was the oldest page, but it was recently referenced. It was recently accessed. So I'm not going to replace it. So I'm going to give this page 0 a second chance. What does that mean is I'm going to put the page 0 at the tail. Okay. And then change the reference bit to 0, back to 0. Okay. So this reference bit, which is 1, just buy page 0 another chance. Okay. But once you actually put 0 on the back, and I reset the reference bit to 0. So if next time when page 0 is actually pushed forward to the head and it's never referenced, then the next time the page 0 will be replaced. Okay. If the page 0 is actually referenced again, then it will give another chance. It will be given another chance. So that means it's, even though it's a FIFO, but the reference bit is going to actually change the order, because if it's referenced, then you will have a chance to stay, and you will not be replaced. But I will actually put you on the back of the tail, at the tail of the queue, so you are not going to be replaced immediately. But I will reset the reference bit back to 0. Okay. So in this case, if page fault happens, I'm not going to replace the page 0. So page 0 will be put on the back. And then I'm not going to replace page 1, right? Because page 1 has reference bit 0. So I put the page 1 on the back and then reset to 0. So now page 3 is at the head, and its reference bit is 0. That means now page 3 is on the front, and the page 3 has never been referenced, never been used. So page 3 will be replaced. That's the second chance page replacement algorithm. It's a similar to FIFO, but you add additional bit. Okay. So this is actually a kind of example. So this is a reference string, and this is the original page, and that's the reference bit. So it looks like page 1 has a reference bit 1. Okay. And the page 0 is currently at the head. I use the arrow. Now, if you have page 2 here, reference page 2 is referenced, and the page 2 is actually in the memory, so it's fine. So what I'm going to do is, well, I'm not going to change the order, right? It's still that order. However, the reference, I'm going to put the reference for 2 is 1. You see the reference bit. The reference bit is set to 1 because 2 is referenced. And then next one, when page 1 is referenced. So 0, 1, 2, page 1 is in the memory, so there's no change. However, the reference bit, page 0 is still 0. Page 1, it's already 1, right? Page 1, the reference bit is already 1, so it doesn't change anything. It doesn't really matter whether the page is referenced once or twice, because there's only one bit, one reference bit. And then when page 4 comes, and page 4 is not in the memory, so then I will replace, yes, I will replace page 0, because page 0 is at the head, and it's also not referenced. So page 0 will be replaced. Okay, so page 0 is going to be replaced with 4, and the reference page is 1, right? And then page 1 it stays, but the arrow going to point to the next one. So it's 1, 1, 0. Oh, I think I put a 0, but because we don't count the initial one. So it's 4, 2, 3. Now, when page 0 is referenced, unfortunately, because page 0 was here, but it was replaced. When page 0 is here, And then the current point, the head of the queue is point to 1, page 1. And page 1 has reference 0, right? So what I'm going to do is, okay, page 1 stays. But I'm going to change the reference bit to 0, right? And then I'm going to move this arrow to the next one. And the page 2. Well, page 2 reference bit is 1. So page 2 stays. But I'm going to actually change the reference bit to 0. And then I'm going to move to page 3. Now, page 3, the reference bit is 0. So that means page 3 is not referenced. So 0 going to replace the page 3. Okay. Any questions with this? So that's the second chance page replacement algorithm. So we're still going to use the queue, but we have additional reference bit. So if the reference bit, if the page is at the head of the queue, so based on the FIFO, it will be replaced. But we check the reference bit. If the reference bit 1, that page will get another chance. So you will put the page on the back of the queue and reset the reference bit to 0. So that's the second chance page replacement. Okay. Now, that's pretty much all for the page replacement algorithm. You're probably going to see many different page replacement algorithm, but these are the main. So the least recently used page replacement is the widely used one. But since it's not efficient, so people actually create variations for the LRU. But everything is based on LRU. Okay. Now, let's actually talk a little bit more about the time and the space efficiency of the virtual memory. Okay. Now, first thing we're going to actually check, one of the actually thing we want to check, the term we're going to check is called the page fault rate. Page fault rate is defined as P equals F divided by T. And the T is the number of memory reference. T is number of memory reference. And the F is the number of page fault. Okay. If the page has been referenced 100 times and there's a 3-page fault, that means it's a 3 over 100. So the page fault rate is 3%. Okay. If the page, there are 100 page reference, but 3-page fault occurs, that's the page actually reference, the page fault rate is 3%. Okay. Now the worst scenario is P equals 1, right? So that means every page reference actually incurs a page fault. Every time when you refer a page, then you have a page fault. Every time you refer a page, you have reference a page, you have a page fault. That's really bad. Okay, I don't like this. Now, when P equals 0, that means no page faults occur. Whatever the number of page reference, 100 times or 200 times, there's 0 page fault. That's the best. That's the ideal case, but it's unlikely case. And also, P equals 1 is not. It's also an unlikely case. Okay. Now, why we care about the page fault rate? Because page fault results in a significant overhead. Remember, when page fault happens, then you have to, save the current page in the memory to the back store, to the hard disk. if the page has been referenced. If the page or updated, if the page is not referenced, then you don't have to do that. So you can just simply discard it. However, then the page fault can also involves load the page from the backstore, the hard disk, into the physical memory. Okay. So there's a two actually possibility. One, if the page in the memory has to be replaced, has been referenced and updated, then you need to save the current page to the page to be replaced into the backstore. That requires the communication between memory and the hard disk. And then next one, you need to load the page in the memory at the backstore, the hard disk, back to the page. I'm sorry, back to the frame, to the hard disk, or to the memory. So that means this is the memory and this is the backstore. So if the page needs to be replaced, then so you need to actually first copy the contents of page to the backstore, and then you need to load the next page to the frame. So you need two communications between memory and the hard disk. That's a lot of work. But if the page is not referenced, then you just discard it. You can skip that part, but you still need to load it. So the page fault is very costly, right? You can think about this. The communication between your hard disk and the memory, it's very costly, you know. The communication between your memory and the hard disk is probably like a thousand times slower than the communication between your CPU and the memory. Okay. The communication between this is 1,000 times fast, or even 10,000 times more, depend on your hard disk. Because if you use old hard disk like your magnetic disk, then to locate a page in the hard disk, you need to actually use the file management, and you need to locate the disk, and then sometimes you can hear the rotation of your physical physical disk, and actually pinpoint a particular location for the file. That's a lot of work. That's a mechanical movement. Okay. Now the communication between CPU and the memory, you basically just actually the communication between two, with the electronic signal. So it's close to the speed of light, but to the physical hard disk, sometimes it's involve a mechanical movement. So you can say, oh, it's fast. The mechanical movement is fast because the hard disk can rotate. The disk can rotate at the speed of 7,200 rotation per second or per minute, for typical hard disk. But that's still extremely slow compared with the electronic signal. So the effective access time is average time to access the memory in the presence of page fault. Okay, so this is the formula. That's the effective access time. So M is the time to access physical memory, and S is the time to process a page fault. And the time of S going to be dramatically larger than the physical memory access. So that's why you want to reduce the number. Make the P as small as possible. Okay. Make the P as small as possible. Okay. Because M is mostly like 1,000, even like 10,000 slower or faster than the page fault. Okay. Now here, Let's take a look at the example. So T is the memory reference. So that's a total page reference. And M is the speed, okay? So M, memory reference takes M unit of time. Okay, let's see. Okay, so now if you have a T memory reference with F page fault, okay, now if the process of the page fault takes S time, okay, that's the process of page fault, and that's the process of just reference, okay, page reference, okay, memory reference time. So the total, let's see. So let's see if we want to make sure to keep the page overhead to less than 10%. Okay, so now F is the page fault, number of page fault. S is the time for each page fault. S is the time for each page. So F times S is a total page fault time. Okay. Now here, T is the total number of page reference, memory reference. And this is actually the memory, the time for the memory reference. So T times M is the total memory reference time. Now we hope the total of page fault time is only 10% of the total memory access time. So then we try to make sure this F times S divided by T times M is less than 10%. Okay. Now, what does that mean? So that means if we actually move the M over here, move S over here, then you got F divided by T is less than M times divided by 10 times S. Okay. Now suppose the memory reference time is 10 square and the page reference time is 10 to the 7th. Wow. 10 square versus 10 7th. That's almost like a 10 to the 5. What is that? So that means the memory memory reference time is 100,000 times faster than the page fault. Okay. So that's a lot. So that means if you want to make sure the total actually page overhead is less than 10%, then the page fault rate, which is F divided by T, that's the number of page fault. That's a number of page reference. Then it should be 1 over 1 million. So that means if for every 1 million page reference, for every 1 million page references, you're only allowed to have one page fault to keep the page fault percentage less than 10%. Okay. The page fault overhead less than 10%. So then you no wonder that page fault is really costly. Okay. Every 1 million page reference, you just reference the page 1 million times, and then there's one page fault happens every 1 million. Then the total time for this one page, the total time for this one page fault will take 10% of the total reference time. That's a lot, right? So that's why we try everything to avoid the page fault. Every one page fault is a very, very costly. It's very, very costly. Okay. Okay. So that's the reason why we want to reduce the number of page fault. That's number one priority. To do this, the operating system has some kind of activity called local control. And so the local control is the activity of determining how many actual processes should be running concurrently at any given time to maximize the overall system performance. Now, to reduce the number of page fault, the best way to do this is reduce the number of processes, number of programs running concurrently. The best scenario is if every process is loaded into the memory, if every program is loaded into the memory, then there's no page fault because every page for the program is loaded into the memory, and then there's no page fault. The worst scenario is you have a whole bunch of page program loaded into memory, and each program only loads a small number of pages, and the majority of the page are loaded. So you're gonna actually incur a lot of page fault. So that's the reason why they have a certain diagram called a thrashing. The thrashing basically means, okay, here's a CPU utilization. Okay, now to increase the CPU utilization, make sure the CPU is busy. That's good, right? Because if CPU is idle, that's a waste of the CPU time. Now, if your CPU is busy, to keep the CPU busy, you want to load more programs. Now, if you load more programs, they're going to be more page faults. So there's a certain ratio, okay, at a certain percent, that's n is the number of concurrent processes. Okay, now there's a certain actually number. So when this n reaches a certain number, then you can maximize the CPU utilization. But after you pass this number, the more program you load, you're going to reduce the CPU utilization because most of the time the CPU is so busy doing the page fault. Now, doing the page fault does not contribute to anything, right? Because it does not do any meaningful things. It's just to replace the page. You replace the page and I replace the page, you just replace the page and does not do any meaningful things. So that's called, actually, this diagram is called a thrashing. And once you reach certain range, so you load more program, load more program, load more programs, and now eventually the whole system is not doing anything, just doing the page replacement. So the CPU spend almost majority of the time doing the page replacement, does not do any meaningful job. So that's called thrashing. So there's a limit. So I think that's pretty much all I want to talk about for the memory management. And the next time we're going to actually cover the file system, okay, the file management system. Okay, I think that's all I want to talk about. So do you have any question?
See you on Thursday, Professor. Thank you.
Okay, see you on Thursday. Let me stop the recording.